And our next presenter is Liam Morrissey. And I see your slides there, and take it away.
Member of Leader, and I'm going to build on what OJ and Bill were kind of talking about a little bit. But we're going to talk a little bit more about the solar wind, but a little bit on the effect that it has on the surface and how important this is for understanding the exosphere and ways we can better simulate the process. So as a brief background, we've kind of heard this a couple of times, but we know the sun emits a stream of charged particles known as the solar wind. It's about 95% H plus, 5% He double plus, and we can approximate it at an energy of 1 keV per AMU. What's unique about the moon, as opposed to Earth, say, is that its surface is exposed to this stream of solar wind impacts. Depending on the energy, the angle, and the impactor, this can potentially lead to solar wind sputtering, where we're going to see the solar wind knock off atoms from the surface. So this process of ion-induced sputtering is important for understanding both the evolution of the surface, so does the solar wind create damage, roughness, etc., along with the exosphere. What is the contribution of these sputtered particles to the exosphere? However, for us to understand this, we need reliable sputtering data to actually constrain the various sources of certain observed species. And in particular, we'll just talk about sodium today as an example. But basically, solar wind-induced sputtering is not the only potential source to emitting into an exosphere. So we need ways of understanding the relative contributions so we can understand what process is key. So like I said, we need this sputtering data, and lab simulations are complex and expensive, so we use theoretical models. The most often are what we see as binary collision approximation. If you've heard of its sputtering simulations, you've probably heard of TRIM or SRIM, and SD-TRIM-SP is kind of a growth on that. But what's key about all of them, and all that you need to know today, is that they require a user-defined surface binding energy, meaning that if you're going to run this simulation, you have to provide the code a defined surface binding energy. So what is that surface binding energy? That's the energy needed to remove a surface atom. It sounds simple, and you'll often see it approximated as the monatomic cohesive energy. However, compound-specific surface binding energies are lacking, and this opens up the question that is the surface binding energy a fixed value depending on the atom type in question, or is it instead a mineral-specific value? Now, BCA methods often assume that bonding to other atom types does not change the surface binding energy. If you think intuitively from a material science point of view, this doesn't really make sense. If the surface binding energy is the energy you need to pull an atom off the surface, obviously as that surface composition changes and bonds change, the strength of that bond changes and the energy you need to remove an atom changes. This can potentially introduce large uncertainties into the predicted sputtering behavior, and today I'm going to kind of demonstrate this. So if we're going to talk about the surface binding energy of a sodium-bearing compound on the moon, we want to think about where are we most likely to see sodium in the moon and in what kind of mineral. Sodium on the lunar surface can be contained in feldspars, which are rock-forming tectosilicates. I've showed you an example here on the right. But basically, in all these silicates, sodium is bonded to oxygen. The problem is that there's no universal approximation of the sodium surface binding energy from such a compound. You can see that there's previous ranges from 0.27 eV based on a sulfate all the way up to about 2.7 eV based on fitting to experimental data. More or less, we don't really know. So how can we find a way to better understand the surface binding energy? Well, what I'm introducing is that molecular dynamics can be a really valuable tool to obtain mineral-specific surface binding energies. What's unique about MD is that it can be used to simulate all the atomic interactions in the system. We're actually taking our scale down to the level of atoms and looking at what's happening to every individual atom using what's known as an interatomic potential. What's key here is that the surface binding energy is not a direct input, but actually calculated based upon the distances, interactions, bonds, and force fields. So the methodology that I'm using is that first I use MD to constrain the surface binding energy of sodium from a variety of different silicates and compounds. And then I take that surface binding energy from MD and I use it as an input into the BCA methods to model the effect of the surface binding energy on the sputtered sodium behavior due to solar wind ions. So to obtain the surface binding energy using MD, I focused on an albite end member along with simple sodium silicates, where I found the minimum energy needed to remove a surface sodium atom, and then I compared that with the substrate's cohesive energy to understand how close are we based on these approximations. I know we're short on time here, so I'll get right into the findings. So we have in our table here on the far left is the substrates used, ranging from pure sodium all the way up to an albite. And in the bold column here is the sodium surface binding energy calculated using MD, along with the cohesive energy of the substrate and the coordination number. right away, we can see that the surface binding energy is highly dependent on the substrate you simulate, ranging all the way from 1.4 eV for sodium removed from a pure sodium surface, all the way up to 7.9 eV for sodium removed from an albite surface. Furthermore, the monatomic sodium cohesive energy, which is what's commonly used in the past, and that's about 1.1 eV, significantly underpredicts the surface binding energy from silicates. Instead, the surface binding energy does appear to be loosely correlated with the mineral's cohesive energy, along with the coordination number of the sodium. The coordination number is basically the number of bonds to oxygen atoms. And as I mentioned, sodium from albite has a surface binding energy 6 times higher than pure sodium. So the important question to ask now is, okay, I've shown you that the surface binding energy is mineral specific. I've shown you it's highly discrepant from the common approximation. But what's important for these simulations is you need to quantify whether this has a discernible effect on the behavior that you care about. So what I did is I took the surface binding energy and I used it as an input into SD trim SP for 1 keV impacts onto albite. On the y-axis, we have the sodium sputtering yield. On the x-axis, we have the surface binding energy. We can see that the surface binding energy does indeed have a significant effect on the yield, with the sodium yield being decreased by a factor of 15 for a surface binding energy increase from 1.1 to 7.9 eV. So big changes in the predicted sputtering behavior. Similarly, it also affects the ejecta energy distribution, basically how energetic is the sputtered atom. I use the Thomson energy distribution to predict the sputtered sodium energy. On the y-axis is a normalized count. On the x-axis is the emission energy of sodium. You can clearly see that as we increase the surface binding energy, we're both broadening the energy distribution and we're increasing the peak. Meaning that, for example, increasing the SBE from 1.4 eV to 7.9 eV saw an increase in the peak by 7 times. Now, this has implications that are really important when we talk about the implication for the evolution of the exosphere. I've shown you that the surface binding energy affects the proportion and yield of sodium atoms that exceed the escape energy. So what we can do is I can plot here on the y-axis the percentage of sodium atoms sputtered above the escape energy as a function of the sodium surface binding energy. However, we also know that with increased surface binding energy, yes, it's more energetic, but there's also less. The yield goes down. So here what I've plotted on the right is the sodium yield above the escape energy as a function of the surface binding energy. And basically what you can see is that increasing the surface binding energy decreases the yield, but increases the percentage above the escape energy, meaning that the composition depends on the surface binding energy of the target along with the escape energy of the body. And if there's one takeaway that I want to find here, it's that the surface binding energy is a key parameter for modeling the contribution, and we need to build on this by considering other minerals, atom types, along with the role of damage and roughness. Thank you for your time, and I'd welcome any questions.
Thank you. We actually have some time for questions,
Hey,
and so if anyone has any.
Thank you.
I don't think I see any in the chat right now. But if people would like to either add them there or use the, I think you might be able to have access to the raise hand function.
Okay.
Feel free to do that as well. Otherwise, this is really great work and really exciting.
Thank you.
Yeah, really exciting stuff. I think this is just one example of how heliophysics is really going to benefit from having more surface observations and more opportunities to go to the lunar orbit in order to get data and get results. And so it's really nice to see all of this.
Thank you. Yeah, one of my.
I see a question.
Oh, go on. Great. Perfect. Yeah. Question.
Oh, no.
No.
I see a question. Yeah. What sort of surface mineral variation did you consider?
So in this case, because I was most focused on sodium, I considered albite, because what we said is surface of the moon is silicates, largely feldspar. So meaning it's going to have some kind of SiO2 bonding structure, and then what the silicate is changes based upon what we're looking at from an end member point of view. So I started off looking at kind of simple sodium silicates. We looked at a sodium orthosilicate. We looked at a sodium metasilicate. The problem is that they're not really representative of the lunar surface. So the most relevant material we thought was albite, because it's a feldspar end member that contains sodium. Where you are on the end member spectrum, like you'll see labradorite quoted a lot. Labradorite is just a balance between albite and anorthite. So still from a sodium point of view, you're talking about albite. So we think albite was probably the most representative. The catch being we did crystalline albite. So how does roughness and amorphous change, and how weathered do we expect it to be on the surface? That's kind of what we did.
Awesome. And then one other question has come up now.
Great.
What would be the primary source of dust in the lunar orbit?
The primary source of dust in the lunar orbit. I'm not sure about that. I don't think so I'm mostly focused on the escape energy. So less say dust and more. Now, yes, it's potential that sputtering could be leading to dust, but we're not as focused, I guess, on dust because there's a lot of other questions with dust, such as tribocharging and levitation and things like that, that affects the life cycle of the dust. So yes, while it is a potentially important source, I guess we're more so focused on the effect on the exosphere, where we can kind of say this is the percentage that gets at the escape energy, such that we can say this is the expected altitude that you could observe it, or this is the scale height as a function of surface binding energy. So surface binding energy has this push and pull where it affects the energy, aka scale height, altitude, but also affects the yield. So you increase the SBE, you get less, but what you get is a heck of a lot more energy. So I guess less.
Awesome. Thank you.
Great. Thank you.
Thank you.